All right, so let's get going on today's class. So today we're going to continue our look at Chapter 5, Introduction to Hypothesis Testing. So this idea was introduced in that special online class that hopefully most of you have been able to watch at this point. If not, be sure to check it out on the YouTube channel because hypothesis testing, especially in the early going, is something that benefits from multiple exposures to it. So we're going to spend a few days on the exact same idea, the exact same kind of procedure, just because it's something that when you see it a few times, it'll finally sink in and it'll start to make a lot of sense. And as promised, we are finally at the ninja stage of this statistics course. So what we're going to be doing from here on out is actual work that actual psychologists do. So this is probably the things that you were expecting a stats course would be. This is the cool stuff that you can do where you take a look at actual psychology questions, take a look at the actual psychology data, and do the same work that other faculty here do in their own research, the same statistical work in order to answer those questions in psychology. And so we're finally at the stage where you'll be doing what a professional psychologist does. And we're also finally at the stage where you're going to be developing many skills that you might use very soon, specifically in your advanced lab. So many of my students right now, they're in the process of collecting data in their advanced lab. And very soon, in the next couple of weeks, they're going to be organizing their data and doing hypothesis tests in order to answer their questions. And specifically, they're going to be going through the same procedure that we're going to take another look at today. So we're going to have a core logic of hypothesis testing recap that's going to be followed with taking a look at that core logic from another perspective. And then we'll take another in-class demo for hypothesis testing. And for this one, we're going to go and take a look at the data from a very iconic psychology experiment, which is Harlow's infant attachment studies that he did on monkeys. All right, so if you recall, hypothesis testing, this is a systematic procedure. This is a set of steps where you analyze the results that you have about a sample, but importantly, and this is something that needs to be remembered always, you're always looking to say something about the population. So you know something about a sample, but you don't want psychology to end there. You want to be able to say something about a population. So oftentimes, you only have access to that sample, and you want to say something about, again, the population. So you have access to a sample of students, but you want to say something about students in general, the population of students. And these conclusions are based on studying a sample. And just so that you are aware of this, in your textbook, they start with the simplified case that will never happen of a single student. We're going to start with a sample of students, for example, more than one, just because that's a correct way to do it, and I don't want you to learn it incorrectly and then have to switch gears later on. And the core logic of hypothesis testing, the answer that you want to get information on is if you took a known population. So we're starting with a known population. It's not very common in psychology that you're dealing with a population where you know the mean of the population and you know the standard deviation of the population. But it does make hypothesis testing much simpler. So we're going to start with that assumption. So let's say that you're dealing with a known population. What you want to know is that if you have a treatment and you were able to apply it to that entire population, would that treatment be effective in changing this population into a new population? So that's the question you always want to answer. If you start with a population, for example, of depressed individuals, and you give them cognitive behavioral therapy, if you are able to do that for the entire population, would they then change into a population of non-depressed individuals? If you gave the population of autistic children a treatment of a very interactive educational curriculum, would that change them into a new population of children that are different fundamentally from the way that they were before. So that's the question you always want to answer. If I do this treatment to a population, will it change it into a new population? If it does, your treatment is effective. Your treatment does something. If, on the other hand, you treat your known population and it doesn't change, that means that your treatment is ineffective. If you take the population of depressed individuals and you give them a treatment and they're still depressed, your treatment does nothing. It's ineffective. Now, the challenge here of hypothesis testing is that we never have access to that entire population. We can't treat everybody to see how things turn out. Instead, what we do is we take a sample from this population, and for this intro to it, we assume that we didn't measure that sample before treating it. It's a silly thing to do, just in case you were wondering. It's just for simplification purposes. But we take that sample from our known population and we treat the sample. We're able to treat 20 depressed individuals with this particular treatment. And then we measure the treated sample, that one we do get scores from. And our decision is whether or not that treated sample has changed enough so that it must belong to this new treated population. So that's all that hypothesis testing is. You take that treated sample and you ask yourself, does it belong to that treated population? Another way to ask this question is not whether it belongs to the treated population, but does it no longer belong to that known population, that untreated population? So if it doesn't belong to the known or untreated population, then it must belong to a new population. So it's the same question asked in a different way. All right, so let's isolate those two. We have our sample from our treated population. We have our treated sample, and we want to know, does it belong to this known population? So here is the kind of key idea behind hypothesis testing. Let's say that that's where our known population is, and let's say that that's where our treated population is. So, sorry, our treated sample is, our sample from the treated population. So there's the mean of your known population, and there's the mean of your treated sample. And you can see that these two have a difference to them, right? There's some difference between the mean of your treated sample and the mean of your known population. And the question we ask ourselves is that difference big enough to say that our sample could not belong to this known population, therefore it must belong to another treated, different population? So that difference can either come about from two different ways. One is that your sample still belongs to the population. So your treated sample, even though we treated it, our treatment did nothing, and our sample still belongs to this treated population. If that is the conclusion we come to, that means that we accept the null hypothesis, and even though our sample kind of ended up over here, we conclude that it still belongs to this treated population. It has not changed. It still belongs to this untreated known population. The other thing that can happen is we take a look at that difference and we say to ourselves, all right, this treated population sample no longer belongs to the known population. This difference is big enough that this treated sample has changed and it doesn't belong to the known population. It now belongs to the treated population. It's fundamentally changed. It belongs to a new population. That means that your treatment actually did something. It took people that were part of one population, that blue population, and it changed them into now individuals that belong to this new treated red population. So in that case, your treatment does something, and we reject the null hypothesis. We reject that idea that our treatment is ineffective. Incidentally, be prepared for a lot of double negatives, because the null hypothesis is that your treatment does nothing. So we have one negative there. Your treatment does nothing. Rejecting the null hypothesis is something you'll read where you deny the idea that your treatment does nothing, so that your treatment does something, right? So our treatment does not do anything, is rejecting the null hypothesis. And then occasionally, and I hate when they do this, you will read about failure to reject the null hypothesis, where it's not that our treatment does nothing. So just be prepared for some double, triple negatives. Don't let it throw you off. If you reject the null hypothesis, you reject the idea that your treatment does nothing, that means your sample has changed and it belongs to that new treated population. All right, so once again, it all has to do with the difference between your population mean, your known population, untreated population, and the mean of your sample, and that's what we can measure. The question now is, how do we use this to determine whether or not this sample belongs to the old untreated population, so your treatment does nothing, or has this sample transformed after treatment and belongs to a new population? How do we make that determination? Well, the core logic of hypothesis testing goes back to that idea of samples and populations. So samples are used to estimate population parameters. You have your sample mean. It's used to predict your population mean. And there's that relationship that we talked about before between a sample and a population that it's from. So if you have a population, you might have a sample that comes from the center of that population. You might have a sample that you can measure that is known, but it comes from the center of that population. Those samples are highly likely. On the other hand, you might have a sample that comes from the extremes of the population, and those samples, while possible, are much less likely. And you can have samples from one side of the population, and you can have samples from the extreme of the other side of the population. But the key thing to remember here is that these samples filled with extreme individuals from the population, extreme scores from the population, those samples are rare. They're unlikely. They have a low probability. And that idea of that low probability is exactly what we use in that logic of hypothesis testing. Because regardless of how much of a difference your treated population has from your known population mean, regardless of how different this treated sample is from the known population mean, there's always two possibilities. One is that difference is due to your treatment. You took a normal sample that was over here, and your treatment actually moved it to where it is right now. So your treatment did something. Your treatment is effective. It took a sample that used to be here, and it moved it over here. That's possibility number one. Possibility number two, however, is that your treatment did nothing and you were always here to begin with. And the way that you ended up there is because when you took your sample from this population, you didn't know it, but you just chose a bunch of extreme individuals. And there is a certain probability that that will occur. And that's what hypothesis testing is. So you either have a treatment that is effective and you took a regular sample and moved it to this location, treatment is effective, or your treatment does nothing and you started with a sample in this location to begin with, so your treatment didn't move the sample, your sample was always there. So that's the alternative kind of view of hypothesis testing. And what we do is we simply ask, what's the probability that your sample, after you treated it, comes from the known or untreated population? We just take a look at our sample and we say, what is the probability that this could have occurred? What is the probability that we might have just chosen extreme individuals from our known sample? What's the probability that our treatment did nothing? We just started with extreme individuals. If that probability is likely, if it's probable that this is what occurred, then we say that our treatment does nothing. If it's highly likely that we could get a difference of this size between the sample and the population by choosing extreme individuals, then we say that our treatment does nothing and we accept the null hypothesis. If, on the other hand, in order for this difference to occur, we would have to get extremely lucky, right, and pick Bill Nye the Science Guy, pick Neil deGrasse Tyson, pick Bill Gates out of a random population. If we needed to get very lucky to pick extreme individuals, well, then the probability of this is highly unlikely, and we conclude that our treatment does something. So if this extreme of a sample is very unlikely, that means that our treatment causing this difference is likely, right? Because it's either an extreme sample or it's our treatment. If the extreme sample probability is unlikely, that means that our treatment probability is highly likely. So our treatment does something and we reject that null hypothesis. So that is the logic behind that. Any questions so far? Okay. So the last thing we need to answer is how likely is likely? So we kind of talked, oh, this has a high probability, this has a low probability. How likely is likely? That is, where is our line in the sand that we're going to compare our unlikelihood to? And that line in the sand, that line where you either cross it or you don't, that is what is known as your alpha level. And your alpha level will be given to you until you get more letters behind your name and you can decide your own alpha levels. But for the most part, alpha levels are given to you, and there's a couple of standard ones that we use in psychology. But if your probability of your sample coming from that known population is greater than alpha, then we accept the null hypothesis. We say there's no effect. So if we have a sample probability, right, and it equals something, and we have our alpha level, and we set our alpha level, this is the most popular one, 0.05. 0.05 means that we were going to accept a 5% chance, right? 5% is the difference between unlikely and likely. Anything above 5% is likely. Anything below 5% is unlikely. That's what that alpha level means. If your sample probability, if the probability of getting a sample this extreme is 12%, right? If 12% of the time that you took a sample from this known population, you would get a sample this extreme, well then our sample probability is higher than our alpha, it's greater than our alpha, and we accept the null hypothesis and we say, look, there's a 12% chance that our sample actually did come from this unknown population, from this known population. So we're going to say that our treatment does nothing. All right, so that's the one side of the line in the sand. If, on the other hand, your sample probability is less than your alpha level, let's say that your sample probability is only 1%. So we have a 1% chance that we got a really, really fluky, weird sample. We just got a really extreme sample. This difference is only going to occur for 1% of the samples from this known population. If we have a 1% chance that we got an extreme sample, that means we got a 99% chance that our treatment caused this difference. So importantly though, this 1% is less than our line in the sand, less than our alpha level of 5%. So in that case, we reject the null hypothesis. We say, yeah, there's a chance our treatment did nothing, but it's so low that we're going to conclude our treatment did something. We reject that null hypothesis, that idea that our treatment did nothing. All right, so again, it's all tied into that probability of the sample from the from the known population. So if your probability of your sample is greater than alpha, greater than that line in the sand, that means that our sample was likely to have come from this known population. Our treatment does nothing. We accept the null hypothesis. If, on the other hand, our sample probability, like right here, is less than our alpha level, less than our line in the sand, that means that it is highly unlikely to have occurred from the known population. That means that our treatment must have changed it. Our treatment does something, and we reject the null hypothesis, reject the idea that our treatment does nothing. So that is the logic of hypothesis testing in a nutshell. Basically, all you're doing is taking a look at your sample that you have measured and asking yourself, what's the probability that this sample could have come from this known untreated population? If the probability is higher than your alpha, you say it's highly likely that we just got extreme individuals. If your probability is lower than alpha, you say it's very unlikely that individuals this extreme would have been chosen from the population. Therefore, you say that your treatment does something. All right, so that was the second look at hypothesis testing. Once again, just a different alternative perspective. So kind of let this sink in. What we're going to do right now is we're going to go through another example, once again, using the hypothesis testing process. So one thing to keep in mind as we go through this process, first thing, it's a 5-step procedure, and this is basically what we're going to be doing for the rest of the semester. We're going to be doing these same 5 steps with minor tweaks for the remainder of the semester. The second thing is that the logic of hypothesis testing, why this makes sense, why we do things this way, is separate from the ability to do a hypothesis test. So this logic here, this will eventually sink in, right? For some students, it sinks in quicker than for others. But this idea of determining between whether this sample still belongs to the known population or is it too extreme, it has to belong to the treated population, that might sink in today, maybe a week from today, maybe a month from today. You know, I can't predict that. However, the hypothesis testing procedure, this is 5 steps. And whether or not you get this, you can still do these. So if you're still kind of struggling with the logic of it, the sense of it, don't let that discourage you. Focus on the hypothesis testing. I oftentimes find that when students do it and work it out a few times, eventually it just snaps and you're like, oh, I get it now. I get what we're doing. But at the very least, this you should be able to do immediately. All right, so hypothesis testing procedure. Let's check it out. Step number 1. Restate the question as a research hypothesis and a null hypothesis about the population. We'll break down each of these steps in just a moment. Step number 2, determine the characteristics of your comparison distribution. Step number 3, determine the cutoff sample score on your comparison distribution in which the null hypothesis should be rejected. That's your line in the sand. Step number 4, determine your sample score on the comparison distribution. That's figuring out if your sample walked across that line in the sand. And then step 5, decide what to do to reject the null hypothesis. So we are today going to build on step 3 and build on step 4 here to determine the cutoff sample score on the comparison distribution and determine your sample score on the comparison distribution. And by way of illustration, we're going to go to a classic psychology experiment that was done with Harlow and infant attachment. So just for a little bit of background on that, let's check out this video of what happened back in, what's this date here, 1959. All right, so this is a classic study from 1959.
Newborn rhesus monkeys will grow up not in accordance with nature, but in the controlled atmosphere of a laboratory, where all the psychological influences of childhood can be duplicated. In a classic continuing study, infant monkeys are removed from the mother at birth and raised in semi-isolation. Other individuals can be seen and heard, but there is no physical contact, no interaction. Mother is a bit of plastic and shaggy cloth, a doll with no life of its own, but capable of nourishing the life of an infant. monkey will come to depend upon this doll to satisfy basic necessities of life. Not only nourishment, but a deeper psychological need for comfort and security. In primate infants, there is an instinctive need to cling to another body, soft and warm. Food or security? Which is motherhood's stronger appeal? Alongside a warm, familiar mother of cloth is a stark wire doll set up as nothing more than a feeding machine. The young monkey is placed deliberately on a cloth mother which has no milk to nourish him, but fulfills some fundamental needs. This experiment revolves around one simple question. Will the infant monkey switch his affection to a wire mother which offers food and life itself? Only when forced by hunger does he loosen his grip and begin to yield to nature's most powerful internal drive. From the wire mother he derives one thing, nourishment. No warmth, no comfort, no feeling of security. After feeding, he returns to spend up to 22 hours a day near the only mother he knows. From this inanimate object, the infant derives all the security and mother love he needs. He can, if also exposed early to other young, grow into a normal, well-adjusted adult.
All right, so that was Harlow's infant monkey experiments, and this is a very influential finding. You probably so if you want to read the original report, which I highly recommend, if for anything you're interested in psychology, always try to find the primary research. This is actually uploaded to Canvas if you want to take a look at it, if this is your area of interest. But this was a very, very influential psychology study because it showed the importance of a parent providing things other than just food. So this was done in the 50s, and if you went back into the 50s and took a look at, for example, the role of the father in the house, if somebody said, you know what, I don't really talk to my kids, I don't really interact with my kids, but I put food on the table, I put a roof over their heads, and I give them clothes to wear. Back in the 50s, people would look at that person and say, you are a great father. Wow. Food, shelter, and clothing, you're hitting it all. 100%. Excellent. These days, if you hear a father say something like that, like, I don't talk to my kids, but I put food, shelter and clothing on their backs, they would look at them and say, you're insane. That is not how you parent. You got to interact with your child. This was the study that highlighted that. This was the study that said things like comfort, things like intangible affection is very important and needed for infants. All right, so let's set this up. So it was a classic study of infant attachment. So Harlow placed monkeys in a cage with two separate mothers. One mother was a mother made from bare wire mesh and contained a baby bottle from which the infants could feed. The other mother was made from soft terry cloth and did not provide any access to food. Harlow observed the infant monkeys and recorded how much time per day was spent with each mother. In a typical day, the infants spent a total of 18 hours clinging to one of the two mothers. So in an 24-hour period, they would spend 18 hours with one of the two mothers. If there was no preference between the two, you would expect the time to be divided evenly, with an average of 9 hours for each mother. So if you spent 18 hours in this cage, and you didn't care whether you spent time with the wire mesh mother or you spent time with the terry cloth mother, you would expect probably 9 hours with the wire mesh, 9 hours with the terry cloth. So if the population of monkeys is such that there is no preference between the two mothers, then the time spent with the terry cloth, right, the time spent with the terry cloth mother would be on average 9 hours, right? Because they have 18 hours in total. So if these monkeys belonged to a population that didn't care which mother it spent time with, then on average, that population would spend 9 hours with the terry cloth mother, 9 hours with the wire mesh mother. What he found, however, what Harlow found, is that typically the monkeys spent 15 hours per day with the terry cloth mother, and that indicated a strong preference for that soft, cuddly terry cloth mother. So let's suppose that we got a sample of 9 infant monkeys, and we found that they averaged 15.3 hours per day with the terry cloth mother. Is this result sufficient to conclude that monkeys spent significantly more time with the softer mother than would be expected if there was no preference? So we got a question to ask ourselves here. We got a sample of 9 monkeys, and they spent 15.3 hours per day with the terry cloth mother. So this is 9 hours. If this is the population that has no preference, all right, so remember, this is no preference. This population here is the population of monkeys with no preference. We have a sample of 9 monkeys that came in with a sample mean right here. We have 9 monkeys that came in with a sample mean of 15.3 hours. So either these monkeys belong to a new population with some unknown mean that does have a preference and prefers the terry cloth. So that's one possibility. We have a sample that is belonging to, and in reality, all monkeys would belong then to, this population over here that prefers the terry cloth. That's possibility number 1. The second possibility is that all monkeys belong to this population. And we just happened to get 9 terry cloth loving monkeys in this particular experiment. So we just happened, by chance, to pick the 9 most terry cloth loving monkeys, 1, 2, 3, 4, 5, 6, 7, 8, 9, in this terry cloth loving experiment. And we just got this extreme sample. So 2 possibilities. Either this sample belongs to a population that prefers terry cloth mothers, or we just got extreme monkeys in our sample. Which one is it? Which population is the actual population? We now turn to the hypothesis test. So the last piece of information we need, we're going to do a two-tailed test with an alpha of 0.05. We will explain two-tailed tests in the coming days, but for right now, we'll just take a look at the hypothesis testing procedure. All right, step number 1. Restate the question as a research hypothesis and a null hypothesis about the population. So we want to know, is there a preference for the terry cloth mother, or is there a preference for the wire mesh mother? And very interestingly, it could be, there's a possibility for both. The wire mesh mother actually gives food, all right, actually gives sustenance. Maybe the wire mesh mother will be preferred. The terry cloth mother is soft and cuddly. Maybe the terry cloth mother will be preferred. So we're looking for just, is there a preference for one of them? Is there a difference between the two? So the research hypothesis, this is the question we want to ask. Cannot attack this with a statistical approach until we restate it as a research and null hypothesis. So the research hypothesis is always that the treatment does something, that there is a difference, that there is a, in this case, preference. So the research hypothesis is that there is a preference for one of the mothers, and that would mean that the average time spent with the terry cloth mother does not equal the average time spent with the wire mesh mother. And that would be written in another way, that the mean for the time spent with the terry cloth mother does not equal 9 hours. So we know that they spend 18 hours in total. What that means is that if they spend more than 9 hours with one mother, they have to spend less than 9 hours with the other. If they spend 12 hours with one, they have to spend 6 hours with the other, because they only spend 18 hours with the mothers. If they spend 5 hours with one, they have to spend 13 hours with the other. And the only way that there's going to be no preference is if they spend 9 hours with one and 9 hours with the other. So as long as one of these levels is not equal to 9, it's going to be different from the other level. And there we have our research hypothesis that the mean time spent with the terry cloth mother will not equal the mean time spent with the wire mesh mother, and neither of those will equal 9 hours. So here we have just one half of that part, whereas the mean time spent with the terry cloth mother does not equal 9 hours. So this is if there was no effect. This is if there is an effect. This is not equal to 9. All right, so that was a research hypothesis. There is a preference. The null hypothesis is always that there's nothing, that there is no difference. In this case, there is no preference. So the null hypothesis is that there's no preference for either mother. The time spent with the terry cloth mother will equal the time spent with the wire mesh mother. And those two, because they have to add up to 18, means that you're spending 9 hours with the terry cloth mother. So once again, this is the population distribution where there's no preference. And you can see that the mean of that is 9 hours because they'll spend 9 hours on average with the terry cloth mother, 9 hours with the wire mesh mother, no preference there. They're spending the same time with each mother. So that's step number 1. Restate the question as a research and a null hypothesis. Step number 2, determine the characteristics of your comparison distribution. We're going to see how to do this in chapter 6. For right now, just practice thinking about this. Your comparison distribution is not the same as your population distribution. Your comparison distribution is that distribution of sample means. And we'll see how to get that later, but for right now, it's got to be given to you. And in this case, the mean of the comparison distribution is 9 hours. The standard deviation of it is 1.76. So that's the comparison distribution. Importantly, not this population here, but the distribution of sample means that you can make out of that population. All right, so set a cutoff sample score or critical value. This is the target against which you're going to compare your study. This is what I like to call that line in the sand. You're drawing a line in the sand, and you're saying you cross this line, and I'm going to reject that null hypothesis. I really will. So this is the line in the sand that you're going to compare the results of your study. We're going to see how to do this soon as well, but for right now, it has to be given to you, and it is a Z critical of 1.96. So you'll notice that our comparison distribution, let me see if I'll get rid of this one right here. All right, so a couple of things to notice here. Your comparison distribution. If we back it up, it has a mean of 9 hours, and it has a standard deviation of 1.76. That's our comparison distribution. There is no table in the back of your book for a comparison distribution with a mean of 9 hours and a standard deviation of 1.76. So what we need to do is we need to take this comparison distribution and we transform it into z-scores. So this 9 hours transforms into a mean of 0. And this standard deviation of 1.76 transforms into a standard deviation of 1. Now you open up that appendix 1. Now you have the ability to answer this hypothesis test. So that when we get to your cutoff scores, spoiler alert, you're going to be looking these values up in your appendix in that table. For right now, I'll give it to you, but these cutoff scores are your critical values. And we have one on this side, and it's at a z-score of 1.96. And we have another one on this side, and it's at a z-score of 1.96. So these lines in the sand, these are your lines in the sand. This is your comparison distribution, Remember that it's a distribution of sample means, right? It's a distribution of samples, not individuals. And what these lines in the sand are saying is saying that all the samples that are in here, these ones are not weird enough for us to say they no longer belong to this comparison distribution. But these samples beyond the lines, these samples over here, these weird samples over here, these are all the wire mesh loving samples of monkeys, 9 monkeys, that just happen to come from this area of your population. These samples over here, these are the terry cloth loving monkeys that just happen to come from this area. So what we're looking is our sample weird enough to have crossed over into one of these areas so that it's a super weird sample, super unlikely to occur, and we conclude that it must be that monkeys prefer one mother over the other. So that's how these lines in the sand work, and in the coming days we'll see how it is that you actually find those values. For right now, I'll give them to you, 1.96 for this hypothesis test. All right, now we determine our sample score on the comparison distribution. This is your z-score for your sample. So once again, we have our sample mean right here, 15.3 hours. That's our sample mean. We know it. But we need to figure out where is it on this comparison distribution. And this is a distribution of z-scores. So we got to take this mean and we got to change it. We got to convert it into a z-score. So we got a mean of 15.3 hours. We have our comparison distribution. Pre-z-score transformation has a mean of 9 hours and a standard deviation of 1.76. We use those z-score formula that we've been using all this time. You take your sample mean minus your comparison mean, your comparison distribution mean, divided by the standard deviation. We put all that in, and we find a z-score of 3.57. So if we take a look at our comparison distribution, and we're wondering, where is this mean on this comparison distribution? So this again is a distribution of sample means. Our sample's in here somewhere, right? We got to find it. So we found that our sample has a z-score of 3.57. This is a mean of 0. This is 1.96. So we go to 1, 1.96, here's 2, here's 3. 3.57 is somewhere all the way out here. So our sample mean, our monkeys, have crossed this line. That means that if they are a sample of terry cloth loving monkeys, we got the most unlikely sample we could possibly get. We got a hugely unlikely sample of terry cloth loving monkeys from this population with no preference. So it's either a very, very unlikely sample from a population with no preference, or this population is incorrect and we just have a regular sample that comes from monkeys that prefer the terry cloth mother. So that is step 4. We find our sample on our comparison distribution. And then step 5 is where we make that final decision. Now, one thing to keep in mind about step 5. Once you kind of get the logic, once you kind of understand the process and it kind of gets ingrained in your mind, step 5 is going to become very straightforward. Until that time, however, step 5 is laden with double negatives and mental gymnastics. So I highly, highly recommend, until you are very familiar and very comfortable with this procedure, take a look at these 2 slides that we're going to go over right now. Keep them handy and help them to make your decision. So if the sample z-score is beyond the cutoff z-scores, beyond means you've crossed the line. You started in the center and you've gone beyond where the lines are. If that's the case, then you accept the research hypothesis and you reject the null hypothesis. If, on the other hand, the sample z-score is within the cutoff z-score, if it didn't cross those lines, if it stayed here in the center, then we accept the null hypothesis and we reject the research hypothesis. You will be surprised how many students do step 1 correctly, do step 2 correctly, step 3 correctly, step 4 correctly, and then fumble at the 1 yard line on step 5. And it's because they're not using these slides. So once we get to this point, we have our distribution, we have our cutoff scores, we found where our mean is. Even if you know and understand nothing about hypothesis testing, it is still very straightforward to say, if the sample z-score is within the cutoff z-score, nope, no it's not. So I'm not going to do this. If the sample z-score is beyond the cutoff z-score, yes it is. There it is. It went beyond the cutoff z-score. What do? Well, I don't know why, but I accept the research hypothesis. Okay. I don't know why at the moment, but I reject the null hypothesis. So if that's where you're at currently, fine. That's completely acceptable. But make sure that you're using these slides, using this kind of decision matrix, because you don't want to do all the hard stuff correctly and then come up with the wrong conclusion because you were juggling, failing to reject the null hypothesis, in your mind. All right, so we are rejecting the null hypothesis is because our sample score went beyond our cutoff z-score. So we reject the null hypothesis. We reject the idea that there is no preference. And we conclude that the monkeys, in fact, do prefer the terry cloth mother. They do need that idea of affection. All right, so that is your second exposure to hypothesis testing, this time with a psychology experiment pulled from history. Are there any questions on that so far? Okay, so as you can see, we're kind of building up this idea of hypothesis testing kind of bit by bit. So far, out of the 5 steps, you know how to do, or you've seen how to do step 1, the research and the null hypothesis. You've seen how to do step 4, calculating your z-score, and you've seen how to do step 5, making your final conclusion. We're going to be introducing steps 2 and 3 as we go along, but this kind of stage of the class, it's very important to kind of see this a few times. So I would highly recommend, if this still is kind of feeling new to you, make sure that you check the YouTube videos. I'm going to put this one up as well. Watch it, maybe an extra time, maybe 2 extra times, because the more you kind of see it, the more sense it will make. And just to alleviate any anxieties that might be cropping up, you can do hypothesis testing without understanding the logic of it at all. So it is completely capable to do these 5 steps without understanding. Now, if you do the practice, if you do the homework, if you're keeping up with class, you will eventually understand it. It will eventually just come to you and you'll think to yourself and say, oh my gosh, I get it now. Oh, if it's highly unlikely, then the treatment probably caused it. If it's not highly unlikely, then it probably did nothing. I get it now. But if you're not quite there yet, don't worry. You can still do hypothesis testing. Just let it sink in. Just kind of let it work its magic and expose yourself to it. Make sure that you are interacting with stuff. All right. So on that note, you'll notice that we still don't have homework due. You can kind of start up on your homework if you want for Chapter 5. But we are going to go over a few more things, specifically one-tailed, two-tailed tests, I believe, next time. So I would say, again, just look over the slides, look over the lectures a couple of times. Let it sink in. Give it time to work into your mind because, again, this is literally what we will be doing for the entire semester. So the more you can kind of grasp it early, the more the rest of the semester is going to be very, very straightforward. Other than that, as always, stay up to date on your pretest points if you didn't get 100% on your pretest, or even if you did, feel free to check out the MyStatLab study plan. For those of you that did not get 100, it's a nice way to boost your grade up to that maximum of 100. All right, so that is what I wanted to cover for today. So if anybody, if you're all statsed out on this Tuesday, feel free to call in an early day. On the other hand, if you have questions about anything that we went over today, if you want to start up on your homework, during this practice time, feel free, call me over if you need assistance, and I'll be happy to help you out. Other than that, I am done what I wanted to cover today.